Mauro?
Yes. Welcome everyone to 75 section of EDP and Applied Mathematics. Today we have two excellent researchers, Clement Mouhot and Yuri Tumstein. To start our section, we call the professor Diego to introduce the speaker Clement Mouhot. Please, Diego.
Okay, thank you very much, Mauro, for the opportunity to introduce Professor Clement Mouhot. Professor Clement Mouhot is a French mathematician, but he's developing his career in UK, in the University of Cambridge. He's an expert on partial differential equation and mathematical physics. He has supervised more than 10 PhD theses, and he has more than around 60 publication papers and more than 2,000 citations. He received many prizes and have been invited for many important international congress, as the ICM in Rio de Janeiro in 2018. So he already have been in Brazil. And today, Professor Clement is going to talk about his talk. He's going to talk about quantitative geometric control in kinetic theory. So, Professor, thank you very much for accepting our invitation, and you have the word. So, thank you.
Here is it. Okay, thank you very much for the introduction. First of all, do you see my screen? Okay.
Yes.
Okay, very good. So thanks a lot for this invitation. It's a pleasure, and it's very nice to see that some of these online seminars created during the COVID pandemics have continued. These are very nice initiatives. So the work I'm going to present today, Quantitative Geometric Control in Kinetic Theory, first of all, it's a joint work with Helge Dietert, who is in Paris University number 7, Frédéric Hérault, who is in Nantes, it's a city in France, Harsha Kudri-Durga, who is in IIT Bombay in India, and the full paper is on the archive, and you have here, this is a shorter presentation note. It's a short presentation if you want to just look at a simpler case. Okay, so the title, I insist on quantitative because it's somehow the novelty of our work, but I will explain to you what I mean by control theory and what I mean by geometric control. It's related to works on wave equations in the 80s, late 80s and early 90s. And I will tell you what we do with these collaborators about applying these concepts to kinetic theory and how we obtain quantitative estimates. Okay, so first of all, what is control theory? The control of systems is extremely old because it's a very, very standard problem of engineering. Think, for instance, you want to control the centrifugal governor in a steam engine so that it continues producing the steam properly. Some control system in a car more recently. More recent technology is how to evacuate burned gases in the chambers in the optimal way. In short, you have many, many situations. I'm not an engineer, so I only know the list of applications, but I don't know much about them. But you have many applications of these concepts. In short, it's when you want to drive a system to do something you have decided in advance. Okay, so the control theory, initially, this is in mathematics now, right? We're talking about engineering here, and now I'm going to talk about mathematics. It dealt first with the control of dynamical systems, right? You have y prime equals a function of y, and maybe a way to control it is you'll say, let's add a little control function. That's one way to think of it. And can I drive my, it's the simplest thing you can imagine. Can I drive my initial configuration y0 to a desired configuration y1? This is the desired outcome. Okay, so control theory is an extreme, of course, if you know control theory, what I'm explaining is trivial, but if you've never seen control theory, the idea is very simple. You want to find the C in order to realize the desired outcome. That's one of the formulation of control theory. Okay, and you can easily see that it appears everywhere in engineering. When you want to force a system to realize a certain final state. Okay, so and indeed, the theory of meaning the equations of control theory appears quite early in the 19th century with Maxwell, Rawls, Sturm, Horvitz, and many others. In particular for governance with the Industrial Revolution, producing energy. So two key concepts, and I'm going to come back to that more and more precisely with equations, are the following. The controllability is more or less what I just wrote. Controllability is more or less what I wrote on an ordinary differential equations. Can you control the system? Can you drive the system to go somewhere by a certain control function? Another concept is that of observability. Can you infer the internal states of the system from partial knowledge? It turns out that these two concepts seem very different, but they are in some sense dual from each other. They are very much related. Okay, observability, controllability. And the goal of controllability is to drive the system to a certain final state. But if the final state now that you want to reach is this y1 is actually secretly you realize that what you want to do is to drive the system to the equilibrium, because this is what you want to do most of the time. Actually, in many situations, really what you want to do is to drive the system to equilibrium. We say you want to stabilize the system. Okay, so you want to really drive the system to equilibrium, the steady state where nothing happens. Okay, now the control theory for PDEs. So now we go to infinite dimension, right? You can always think of a PDE as a differential equation in infinite dimensional functional space. But of course, saying that is not really helping you much for proving anything, but it's nevertheless true. It was introduced in the 60s, 70s. Largely by the Italian and French school initially, but then in many other places in the world. And it was a source of many super interesting problems. So the key problem of controllability becomes analyze whether the solution to a partial differential equation, right? So dt, I will call it f to insist that it's a function. And now you have a certain operator of f. And now you want to drive that. Maybe you have a control function here, or maybe you turn on and off here. Sorry, you turn on and off the operator in some part of the domain. There are different ways to, tune the equation. And you want to know whether you can drive f to a final state. For instance, a given final state, or for instance, the equilibrium. Okay, and often you want to apply the control, or you want to restrict the active part of what drives the function to the final state to a smaller part of the domain. That's what is interesting. Now, there's a key distinction to make. I'm almost done with the very general introduction. I'm going to do equations in a second. There's a key distinction to make between time reversible PDEs and time irreversible PDEs. The latter, these ones, are usually significantly harder to study, but also more interesting mathematically. The reason is that one thing you can think of, for instance, for time reversible PDEs, for instance, it's enough to know how to drive any initial state to one final state, for instance, 0. Because then you can reverse that. And now you can drive F0 because F0 was arbitrary. You can drive F0 to whatever else you want. You go through 0 and then you go to another state. Right? So if you just try to reach 0, it's called null controllability. There are other examples showing that time reversible PDEs are a bit less difficult, but that's one of the examples. Obviously, you wouldn't be able to do this for a parabolic equation. You realize that this would be absolutely forbidden. You can't reverse the Cauchy problem for a parabolic equation. Okay, so however, one point that is important and that will show up in this talk is that when you consider time reversible PDEs, they have typically a speed of propagation associated to them, right? Typically speed of light for wave equations in cosmology and or speed of sound in fluid conservation law for fluid mechanics and so on. They are speed of propagations. And that complicates the matter for control. You realize that if your subdomain is in a place, you need some time for the effect of the subdomain where your control acts to reach the rest of the domain. All of that is very intuitive. Nevertheless, it creates a lot of beautiful mathematics, but the starting point is quite natural. And as I said, the control theory of dissipative PDEs is more intricate usually. Okay. I'm going to look at this more complicated case of dissipative PDEs, and I'm going to look at a class of dissipative PDEs that is ubiquitous in statistical mechanics, gas dynamics, and in fact, that is underlying a lot of fluid mechanics. I'm going to look at a class of linear kinetic PDEs. They will be dissipative because of the effect of collisions, whether the collisions are modeled like shocks between balls or in a more diffusive way, but my equations will be dissipative. And I will be looking at this question whether we can prove that the solution is driven to the equilibrium when the collision, the dissipation, the collision and effect are only occurring in a subdomain. So imagine, one way to think of it is imagine a gas, and in a portion of your domain, there's a lot of collisions, and in the rest of the domain, there's no collisions. For some reason, there could be a medium. So there is thermalization here. Thermalization is the name in statistical mechanics for the effect of collision, and pure transport outside. Do we know whether the distribution, the solution to the transport plus collision in this box will nevertheless reach a constant stationary equilibrium? So that's the question. Of course, now I'm going to formulate it better. And these questions are connected to an extremely old and famous area of PDEs, both for hyperbolic and parabolic and elliptic PDEs, the questions of unique continuation. Asymptotic behavior of couple systems, spectral properties is connected to a lot of things in PDE. And in particular, it goes back. So it looks like I'm looking at subcases of the controllability, but in fact, what I'm really looking at, and it goes back to one of the two concepts I introduced in the beginning, is that of observability. So imagine f, the time is the index. So ft is a solution to a PDE. to the PD I'm considering. This inequality is really a linear, quantitative, unique continuation property. I'm telling you that I really know how to estimate the size of my initial data from the size of the solution for an interval of later time, right? So F0 at time 0, then I'll look at the whole solution here up to time t. And of course, it implies that if the whole solution here is 0, then the initial data is 0, obviously. So that's would be the unique continuation, but it's quantitative. It tells you something more precise than that. Okay, so that will be the sort of things I'm interested in. Yeah, that's just what I said. It's a linear quantitative version of the unique continuation principle. And it implies that I will explain that in a second. It will be very much connected to the rate of relaxation to the asymptotic state for the solution to the PD. And this observability inequality is dual in a way, that's what I'm saying, to the controllability. Okay, so to summarize this very general introduction, I'm going to look at kinetic PDEs. I'm going to look at very old questions. It looks like I'm going to look at something very specialized, which is how the solution is driven to the equilibrium. But in fact, secretly, I'm looking at a class of functional inequalities that are more interesting than that, and that are the linear quantitative observability, and it is dual to the controllability of the problem. So I'm actually really, in fact, secretly solving the initial question I'm telling you for this class of equations, and in a quantitative way. Okay, and in case you would have these sort of things non-quantitatively, as in if the right-hand side goes to 0, then the left-hand side goes to 0, you would recover the unique continuation, but in a non-quantitative way. So it all matches properly, if you want. Okay, in my case, there are some complications because the PD is irreversible, and it will be in the case I'm interested in hypoelliptic, but we're going to talk about these complications in a second. Okay, so let's put some equations behind all that. So F, statistical mechanics, is based, so it's a field created by Maxwell and Boltzmann and many others, but mathematically, I mean, the equations are invented by these two physicists. So the main object, the unknown, is the distribution of particles in position and velocity. So F depends on time. I will often put the time as an index to make equations more compact. So be careful, the index doesn't mean I differentiate in time, as people often write in fluid mechanics. And I've got a position and I've got a velocity. And it has to be non-negative because it's a distribution, and it will typically be integrable. However, here I'm looking at the linear system. So because it's linear, you can look at fluctuations. So we won't really be imposing anything on the sign just because the equation is linear. You can superpose, you can do whatever you want. The transport operator T is the Poisson bracket with the Hamiltonian. So let's write it explicitly. It means really that your T is, so Poisson bracket with this Hamiltonian means V dot grad X, right? dV of that times grad X minus the X grad X of that times grad V, right? So this is my transport operator. I wrote it, I tell you, I define it first like that for you because I think it immediately gives you the intuition of what it does. It's a transport operator that creates characteristics where this Hamiltonian is preserved, right? The Hamiltonian is the energy of the particle and it's preserved along the characteristics. It's built for that. The operator L is the collision operator. So it acts only in the velocity variable, And typically we'll consider linear Boltzmann, which is also called scattering, or the generator of a jump process. You have it has many names, but it's like an integral operator that projects upon a certain average in velocity, or the Fokker-Planck operator. I will illustrate really the sketch of the argument with the Fokker-Planck operator in this talk, because it's by far the most interesting mathematically. The spatial dependency is what I'm adding here, and this is where we'll have some control theory entering into the game. This is what makes the question more interesting. So that's what I told you, that the system we're looking at will have a thermalization in a path. Let's say sigma will be 1 here and sigma will be 0 outside. So there will be collisions here and pure transport outside of it. Okay, we have a domain omega x in x. So that's here, the picture I draw is for the spatial domain, and the velocity belongs to omega v. So what could it be for the velocity? Typically, the things you want to consider would be the two most physical things would be either the velocity or in r d. D is your dimension, so maybe let's say r3. So that's the Newtonian mechanics standard velocity of a particle with a mass. Or if you're in a relativistic setting, you will take an open ball. But also a very interesting case is if you're in a relativistic setting, and if you consider massless particles, photons, then you will be in a sphere. Okay, because all particles will have the velocity modulus will always be constant. These are typical cases we want to consider, massless particles. Okay, so these are, I will really, this case is easily obtained from the two other cases. I will focus on this one and this one. Okay, so now we assume, which is true, always true in the physical cases, that this equation admits the following stationary solution. I use equilibrium because the equation comes from statistical mechanics, but in other fields of PD, you would simply call that a stationary solution. The key point is we will prove that it's the unique one when we have the control condition. So the equilibrium is given as a Gibbs measure from the Hamiltonian, if you know what it means. If not, you can just read what the formula is. It's exponential minus phi of x minus v squared over 2 divided by a certain normalization constant z. And the question we want to solve is the following: is this equilibrium unique? And actually, we want to prove better than unique. Is it attracting all solutions, and at which rate? For instance, because it's a linear equation, is there a spectral gap, and do we have exponential rate, and can we estimate the exponential rate? When sigma is, let's say, 1 or is bounded below everywhere, this question was solved in a quantitative way by the theory of so-called hypocoercivity, by the combined effort of many people: Gouault, Hérault, Neer, Villani. I'm trying to respect more or less a chronological order. Villani, and at the same time myself, and typing Liu. It's slightly different, but it's conceptually related. You and you, and many others. But here the questions we will be interested in is the case where this sigma is 0 in part of the domain. That's what I mean by degenerate. Okay, so there are a few works on that when we assume that L is the so-called linear Boltzmann operator. So what it means is that L is just, let me write it more explicitly. So you see rho is just the velocity average of F. Don't forget the unknown has two variables, position and velocity. So this operator L really means you integrate over your velocity space. So I should have written omega v in general. sorry, it's a typo, to make this formula more general. And here I'm integrating f of t x v. I'm multiplying all that by my Maxwellian, meaning the equilibrium distribution in V, minus f of, so because I'm looking that at, I'm going to call that V star, and this is L of f at txv. So for those of you who would have a training in probability, this is really the generator of a jump process, a very simple Markov process with an exponential clock. Regularly, when the clock rings, you just draw a new velocity according to this distribution. That's just what it means. And this is a statistical mechanics evolution equation for the effect of collision with the medium. So inspired by a seminal paper by Bardos, Lebeau, and Roche in '92 for damped wave equations, the first works are due to Bernard Salvarani and Hanquan Leoto, should be a D here missing, who studied this equation, and they proved that, and here, this is what I'm going to explain in the next 5 minutes. If you have a geometric control condition, let's say GCC, then you do have the convergence of your solution towards F infinity. In particular, this is unique. Everything is attracted to this F infinity. This is the only stationary solution there. But if you have a uniform geometric control condition, you'll see in a second what these two concepts means. Then you have an exponential, convergence. However, the proofs, one of our first motivation was we proved more than just answering this question in the end, but that was one of the first motivations for our work. The proof in these two papers, this and that, were based on compactness arguments. And for many reasons, you want to quantify things, if only to understand things better. There was then a work by a former PhD student of mine and a former postdoc of mine. When they were in Cambridge, they could give an alternative argument by probabilistic methods, which is very nice and quantitative, but it doesn't give you really PD estimates. So let me explain what geometric control condition means, first in equation, and then I'll give you some drawings. If we adopt a Lagrangian viewpoint on the evolution, it is made up of two parts. There is the effect of the transport operator, and the transport operator just pushes the distribution along the characteristics. The characteristics are these curves, okay, that are obtained by the Poisson bracket with the Hamiltonian, right? Standard symplectic mechanics, if you want. Then the second part of the evolution is the thermalization and the velocity variable, this operator L multiplied by sigma. But the way you thermalize the velocity depends on the rate that is a function of the position. So it's an interesting dynamics. You see, you move along the characteristics, and depending on where you are, and it will change with the flow, with the transport flow, you will have thermalization or not. So the geometric condition is the geometric control condition is the following. It tells you that all trajectories have to go through the support of sigma, meaning that all trajectories will have to go in a place where velocities are thermalized. Or let me repeat it in yet another way. All trajectories have to go in a part of the domain where there is dissipation or where there is this control acting. The control is acting. The control for us is the thermalization. The uniform geometric control condition is the same, but you want a time. You want to be able to put your hand on a time and a constant so that during this time, all trajectories spend a significant fraction of time in the support of sigma so that you have this bound. The integral of sigma along the characteristic is bounded below. This is really the Bardos, Lebeau, Roche condition. like all great ideas, it's very simple, but of course, it's only simple a posteriori when it's done. It's really quantifying the interplay of a region of the domain with a certain flow. It's formulated with the B characteristic of the wave equation in their paper. Here we formulate it with the characteristic of the transport flow. I just make a small remark in case there is a question. We can go back to this, but it's a small point. I don't want to include it to not confuse things. But if the support of sigma had several connected components, you would need, on top of this condition, you would need some characteristics connecting them. Otherwise, you could have weird situations where you thermalize towards different equilibrium in each component. Okay, so that's what I mean here. Let's forget that, and let's assume that the support of sigma is just made up of one connected component for the rest of the talk. Now let me illustrate what it means. On the left, you have a uniform geometric control condition. So I'm looking at photons. So particle with velocity whose modulus is always 1. Well, 1 is being, in fact, the speed of light, but I just normalize it to 1. So you look at the picture on the left. If you're a photon here, whatever you do with your speed with velocity with modulus 1, whatever you do, you will enter the green hashed area. And you even can quantify how long it will take you to enter it. And it's bounded above how long it will take you to enter the green zone. And then you can bound an amount of time you will spend in the green zone, which is bounded below now. So this is how you prove the uniform geometric control condition. Now, if you look at the picture on the right, in fact, you will still satisfy some very degenerate control condition, but it's not uniform. Because you see, if my photon happens to be exactly following an horizontal speed, it will never enter the green zone. Obviously, such speed has measure 0. Right? So you will, if you remove this measure 0, there will always be a little angle, and at some point, you will enter the green area. I forgot to say that my domains are periodic, sorry. Okay. And you realize that by making your velocity closer and closer to being horizontal, the time needed for entering the green zone gets bigger and bigger and goes to infinity. This is really a degenerate control condition, meaning you will still satisfy this, but not this. And this is reflected at the PD level and the fact that the linear operator will have a spectral gap on the left, with the left picture, and will not in the right picture. There will be continuous spectrum, and we will end up with a polynomial rate of decay only. Okay, so the specific difficulties with the Foucault-Planck operator now, which is really what I'm interested in. So you take L to have this form if you take velocities in R3, for instance. I mean, 3, let's say general D, or you take L to be the Laplace-Beltrami, Laplacian, if you take the velocities to be evolving in the sphere. Okay? You just, it's easy to prove that these two things are conceptually the same thing depending on the space of velocity you choose. The first one has a relaxation effect, a thermalization effect towards the Maxwellian. You can check that. And velocity, this is the only thing that is in the kernel of this operator. And this operator relaxes towards the constant on the sphere. But this is only in the velocity variable. Don't forget, we are dealing with equations where the unknown has 2 variables. It turns out that this operator, this one or the Laplace-Beltrami, I mean both, even though I wrote only one, they give rise when you combine them with the transport. So now you'll put everything. they'll give rise to hypoelliptic PDEs. So if you've never seen this term before, hypoellipticity means that your equation will still have some regularizing effects, but is actually not parabolic elliptic. I mean, that's not you fail the ellipticity criterion, of course, because here you only have ellipticity in V, and this is hyperbolic. So there is no ellipticity in the X variable in your equation. Okay, so that creates a lot of complications. Let me speed up a bit. So the theorem we proved is that if you have the geometric control condition, you have convergence. But more interestingly, if you have it uniformly, we prove exponential convergence to F infinity, and we do it quantitatively. We relate the rate to the control condition. And there's also something, but I don't really have time to talk about it, so I'm really short on time. Let me skip the second theorem and focus on the first one to give you some ideas. Okay, so how much time do I have for the discussions of the proof?
Around 10 minutes.
Okay, so I'll try to give you an idea. The key idea is that we developed a method which solves the question we wanted to solve, so that's good, but is also actually reproving in a different way, very simple way actually, most previous work on linear hypocoercivity. So the method is actually very general, and the key idea is to do a method really following trajectories as much as possible, instead of to avoid as much as possible commutator estimates, which are typical of Hermander style theories, and which were the way to prove hypocoercivity typically in the work of Hérault, Nier, and Villani. So let me try to sketch some idea. We want to prove that Ft goes to F infinity. First remark is that my equation preserves the global mass. Let me just convince you about that. Okay, let me write it below. It's a trivial remark. It should be physically. Let me write the left-hand side a bit more explicitly, because you know it's a statistical distribution, so the total number should be preserved. But let's check it. I'm writing really what the equation means. So here, don't forget it's phi of x. And this is equal to the left-hand side, which is the sigma of x. And for instance, let me write Fokker-Planck in the whole space. But we could write also the Laplace-Beltramian on the sphere. If you do integrate this equation in x and v, you will realize this gives 0 when you integrate. It's a divergence in x. This gives 0. It's a divergence in v. And this gives 0 because it's a divergence in v. So in other words, the total integral is not changing with time. And the problem is the equation is linear. So what we're going to do, just to make our life simpler, we're going to bring back the final state we want to reach to 0. How so? Well, we just consider an initial data with 0 global mass. If it's not the case, you remove to F0 the global mass of F0. Let's call it let's call it M of M0, F0, times the equilibrium with mass 1. Okay, and you create what you want. Don't forget it's a linear problem. You can always remove an element of the kernel of the operator to be in the orthogonal of the kernel. That's only what I'm doing. Okay, so in other words, we are going to the orthogonal of the kernel, if you like more linear intuition. So now the goal is to prove that Ft goes to 0 as t goes to infinity. Another concept that I want to introduce is that of local equilibrium. So that means you project on the kernel, this time in V only, of the operator L. right? So the kernel of in V only is, you have to compute the function that is in the kernel of this operator for V, and that is this Maxwellian V. So typically for the operator I wrote, don't forget that would be something like that, where you can normalize it, and then rho of X is the mass of F. You can check that it's actually really an orthogonal projection, provided you work in a space with a measure m-1. Anyway, I don't have much time to, but trust me, it is a nice orthogonal projection. You define a norm. So F infinity, now it's a norm in X and V. So it's not just m-1, you really consider exponential. So it's 1 over exponential minus Vx minus V square over 2 with the Z. So it's really this. So you see what I mean? This is the weight I put. And for this norm, you have a symmetry structure. So if you wonder where it's coming from, this is really just the linearization of the theorem of Boltzmann about the H theorem of Boltzmann about the entropy. Anyway, we are looking at linear kinetic equations, so they are simpler, but the theorem about the entropy of Boltzmann, if you linearize it properly, you end up with a Lyapunov function, which is this L2 norm with a weight. And you can exactly see what is the associated dissipation function, and it's what I wrote here. So here I wrote it when the velocities are in the whole space, or, so it's -1, when the velocities are in the sphere. In both cases, using very simple Poincaré inequality in V, just in the only in the velocity space variable, you end up with the so-called micro-coercivity. Okay, so if there was not this thing, you would be done for proving the exponential relaxation. But of course, you have this local projection. And now it's complicated by the fact that this coercivity degenerates outside of the support of sigma. So the first argument, I put a first argument for pedagogy, but maybe I will only show this slide and show just 1 second slide to end the talk with the quantitative argument. I won't have to go time to go in more details. The idea is the following. That is the goal. We want to prove this. This is what I told you was the observability. Just note that the observability will imply exponential decay. Why? Because this is, the dissipation is, so don't forget that the dissipation is minus d over dt of the, of the weighted L2 norm I'm looking at. Okay, so if we call this thing y of t, what I just wrote here is y of tau minus y of 0 is greater than, no, I wrote it wrongly. Sorry, there's a minus, so y of 0 minus y of tau, because there is a minus here, okay, is greater than lambda y of 0. If you put it in the wrong way, you put the y of tau to the right, you end up with y of tau less than 1 minus lambda y of 0. This is strictly less than 1. If you iterate it, you obtain y of n tau less than 1 minus lambda to the n y of 0, and it is an exponential rate of decay. I mean, it's easy to convince yourself. If you would call that t, in fact, it means you have proven almost, I mean, you just have to modify the constant a little bit, but you have proven exponential. N is just t over tau, and you have a log 1 minus lambda, right? And this is negative. So this is an exponential decay. Okay, so that's our goal. The first idea, in fact, we didn't finally publish this argument because we got a better argument, but just, it was the first step. You can do a contradiction argument. You consider a sequence that negates your conclusion. So a GN sequence of solution so that the initial data is normalized, the global mass is 0. The left-hand side in my inequality here goes to the left-hand side here goes to 0. And so now it will be a G. The left-hand side goes to 0. The right-hand side is normalized to 1. Okay, so I'm violating my inequality. By weak compactness, which of course is always true, I'll get a limit in L2. I have my solutions will be bounded because the L2 norm decreases. It's very easy to prove that the weak limit is actually 0 by studying the stationary problem. And then you will be able to prove that the initial solution strongly converges at time 0. And for that, you will have to combine averaging lemma and following the trajectories along the dissipation. If you don't know what averaging lemma are, they are invented by Agoshkov and Goltz in the late 80s. And they are a very nice idea that tells you in a nutshell that when you look at an hyperbolic operator like our transport operator, it doesn't work for all hyperbolic operator, but the transport operator we have, if the right-hand side belongs to L2, the hyperbolic operator is not elliptic. dt plus tau is obviously not elliptic, but the singular set, if you want the cancellation of the symbol of the operator, are localized, and they are transversal to averaging in velocity. So when you average in velocity, you retain some little amount of ellipticity somehow. So this will be in h1 half in t and x. You can search for a proof in Fourier if you want. It's a fun game. The proof in Fourier is less than a page. It's just because when you average in V, the bad area where the symbol of your hyperbolic operator is vanishing, where the singularity propagates in the hyperbolic evolution, is a small set in V. So the averages make the influence of this bad set small enough that you still retain some amount of regularity. Okay, and I'll skip the rest of the details on the contradiction argument, and I'll just talk about the argument with fully based on the trajectories. Sorry, yeah. So when you want to do everything along the trajectories, you restart from your observability inequality, and you write a GML formulation with a certain test function that you construct well. See in a second. I will tell you how to construct this test function in a second. And S is the transport flow. And you write the GML formulation along the transport. Okay, I'm sorry because my time is running out, so it will be a bit technical, the last slides. But it's really the GML. No, sorry, here it's not yet GML. I'm just differentiating in time. It looks like a Trotter-Kato formula if you want it. I'm just differentiating in time. There is time here, time S here as well. And I have a test function that I built, and I obtain term 1 due to the transport, 1 due to the collision. I mean, just compute that. And my test function is built cleverly as follow. I take, if I have a function key that satisfies my uniform control condition, that means that my key will be satisfying these when along the characteristics. So this is the control condition written slightly more abstractly. You look at it along the characteristics. The function psi is literally just a normalization of that. It's built so that instead of C, you get exactly 1 all the time. You can do, the fact that you can do that is very nice, and it's due to the reversible nature of the transport part of the equation, only the transport operator. And now you have 3 terms, and I will just tell you conceptually what we do on each of them. So this one is controlled by the dissipation. because you have the collision operator. Now, for this one, it controls from below t times the norm of f0, because if you look at it properly, this sums to, 1 over t, this thing sums to 1. So there's no 1 over t, so it gives just t norm of f0. And now the point is to prove, the goal is to prove that this last term is less than the integral of the dissipation. Here it's the integral of the dissipation. And that is done, so I skip some error terms. I just want to arrive at the main thing. That is done by removing the averages and using, so because I can't show the whole thing, I will show only the functional inequality that makes everything work. That's the, let's say, most novel part of our work. We reduce everything to using the so-called divergence, what we call the divergence inequality. So U here now will be a domain in space and time, space and time only. And we reduce entirely the observability inequality and therefore the spectral gap to the following functional inequality. This inequality is very nice. We extend the results of Bogovsky and Bourgain and Bresis, but they are the one who really proved the first versions of this inequality. We extend it with a weight and with more general domain, but it's really using their ideas in a way. So if you give myself a function g, and I'll stop on that slide, if you give myself a function g in a certain domain u, so for the moment, for that theorem, U is any domain of Rn. For the application, U will be a cylinder in space and time for us. Okay, that's what, that's what U would be for us. Then you have U with 0 mass on a certain domain of Rn, then L2 with a weight. Then there is, it's not unique, obviously. There is a vector field so that the divergence gives G. And the vector field is 0 on the boundary. And you have the natural ellipticity estimates you would expect. So I insist on the fact that this is what makes the theorem non-trivial. Without, if you only ask that the vector field is 0 against the normal, the outgoing vector, this is the Neumann condition, then it's super easy to prove. You just solve it by solving a Laplace-Neumann problem. What is really hard is to get the vector field to be fully 0 on the boundary. And we really need it in the proof. It is a very nice inequality, which is a sort of mother inequality of many others. Poincaré-Lyons, Stokes inequality, Korn inequalities in mechanics. And yeah, I will stop here because I'm already late. Thank you.
Thank you very much, Professor Clement Mouhot, for this very nice talk. So we open now the turn for questions, comments. So if anyone has some question, please just open your microphone or type your question in the chat. I have one question. I mean, in your theorem, you write that if you have the GCC, then you have L2 convergence, right? But
yeah.
do you know if it is necessary and sufficient condition to have L2 convergence, or you have some example where
yes, it's a good question. Yes, there are answers to this. Let me show you. Where was it? In the beginning. Some things remain to be proved. Yeah, that's so here in the previous work that were Bernard Salvarani and Juan Leoto when L, only in the case where L is this integral operator, they prove that it's an if and only if. Now, in the Fokker-Planck case, I mean, actually, your question is related to the part I skipped. Now, if the right-hand side is Fokker-Planck, which means you introduce hypoellipticity in your PDE. Where is it? It's a yes, sorry. It's our second theorem that I had crossed. Things become more complicated. So we proved, for instance, that it's not really answering your question, but it shows that things become more complicated. We gave a case where there is exponential convergence of spectral gap without the uniform geometric control condition. Now, when the geometric control condition is fully violated, I don't think we wrote it, but it's a good question. I do think that you can prove that there is there's no convergence to the equilibrium. So you see, I mean, I don't know if you meant uniform or not. If you mean not uniform, if you completely violate the control condition, yes, you should be able to prove that there is no convergence asymptotically. But if you mean with the uniform geometric control condition, when you look at this integral operator without hypoellipticity, they have proved that it's equivalent to the existence of a spectral gap but it's not with hypoellipticity.
Thank you.
I would like to ask a question.
Yes.
It's more out of curiosity if it does make sense, and if so, like if you would expect to have convergence results in other topologies, like other than L2.
Yeah, it's again, it's a very, very good question. It's related to a body of work. The typical space, which is interesting, bigger than the space. I'm looking at a space that is actually quite small. L2 with a huge weight. So my weight, let me write it as an integral. I'm looking at initial data so that this is finite. So you see what I mean? Typically, phi will be growing at least linearly so that you have Poincare type inequality. So it means you're looking at functions which decay at least exponentially in X and decay like Gaussians in V. So it's a very small space. It's a space with a very strong decay. The space that would be the best at a physical level will be, assuming a sign, of course, otherwise nothing makes sense, to have a space where this is finite. So you can have a functional analysis in that sort of space. I mean, it's an entropy functional, but the corresponding space is called the Hurwitz space, and there are some results in this. So in this sort of topology, there was a result of Villani for the Fokker-Planck case, but without the degeneracy. So the sigma was 1 everywhere. And a former student of mine, Joe Evans, extended the theorem of Villani for the case of the linear Boltzmann, the integral operator. Now, when sigma is degenerate, I don't know. It's not done to my knowledge, but it would be an interesting question. So yes, I mean, the short answer is that it would be interesting to have norms that demand less on the solution.
Great, thanks.
Okay, so is there any other question or comment? So if not, let us thanks again, Professor Clement.
Thank you.
Very nice talk. So I give the word now for Professor Mauro Rincon.
Thank you, Professor Clement, Diego. And now